Welcome to the Are You GCSE Physics Ready playlist. This playlist is packed with example questions and guided solutions for every GCSE Physics topic. So it's the perfect tool to help you test your understanding. If you feel like you might need a quick review of this topic before having a go at the questions, or you would just like the ideal revision companion for these videos, then do make sure to download my free GCSE Physics revision notes, linked in the description below. If you're ready, let's dive in. Okay, let's do some questions on reflection. So we have a ray diagram here and we need to complete the ray diagram. So that is some light coming towards the mirror and it's going to bounce off the mirror. So I can fill in my reflection ray like that, and I know it should be in that direction because I'm looking for that angle of incidence, or the angle between that initial ray and my normal, that line which is 90 degrees to my mirror surface, to be equal to my angle of reflection, that angle R there. So then when it asks me to draw another diagram with a smaller angle of incidence, my diagram should look like this. Okay, so I've got that smaller angle of incidence, which gives me a smaller angle of reflection. And if I'm doing this perfectly with my protractor, those two angles should be the same size. So our law of reflection, angle of incidence equals angle of reflection. Okay, so now we've got a few different diagrams and we need to complete them. So let's look at A on the left hand side first. So that ray is coming towards the mirror and we need to say, okay, which direction is the reflected ray going to be in? So it's going to be in this direction here, which might not seem too obvious to you, but what you really must do in these ray diagrams is if you add the normal, that dotted line there, which is 90 degrees to my mirror, and then I add that angle of incidence from the black incident ray to that normal, then I can see that that angle of reflection there is correct, okay, from my green line to the normal. Okay, now in part B, I've got this three mirror situation going on here. So I have this initial incident ray, which is my black line coming here. That is going to get reflected. Okay, so that reflected ray then goes up to that top mirror. And now that's my angle of incidence, which gets reflected again, back down to that bottom mirror and reflected again, back up and out. Okay, and I need to make sure for all three mirrors, those angles of incidence are equal to the angles of reflections. So you can use reflections to bounce light off surfaces and it can travel from side to side. Okay, and then part C here, where I have my light ray and it's gone directly down the normal. So in that case, since it's travelled down through the normal, then my angle of incidence is actually going to be 0. There is no angle between my incident ray and the normal, which makes my angle of reflection 0, which means that this ray would just bounce straight back up in the same direction. Okay, now let's look at some refraction. So we've got to complete the following diagrams. So I'm going to start again with the one on the left, and we have got some light travelling from air and then it's going to hit that boundary between air and glass. So let me put in my angle of incidence first. So that is between my incident ray and the normal. And then I need to think about the fact that it's going from air to glass and this is a light ray. So because it's travelling from something less optically dense, my air, to more optically dense, my glass, it is gonna be travelling slower. Okay, and then I can use that acronym in the notes to help me. FAST. Fast, away, slow, towards. So if it's slow, then it needs to bend towards the normal. So I need to draw in a ray such that the angle of refraction there between the normal and my line is smaller than the angle of incidence. Okay, let's look at the top diagram here with my semicircular block. And again, I'm going from air to glass, so my light should be slowing down and bending towards the normal. So let's put in my angle of incidence first, And then I just need to make sure that that angle of refraction is smaller than the angle of incidence. And then I've written normal at the bottom here because as that light ray now continues through my semicircular block and then would come back out into the air, it actually goes 90 degrees to that boundary between the glass and my air. So it will just carry on in that same direction as it comes out into my air. Okay, and then I had the classic example of this glass block and a ray of light coming in from some air to the normal. And let me draw in that that is my angle of incidence, and then I'm going to get this picture, okay, where it gets bent towards the normal, and then on the other side of my material it goes from glass back into air. So this time it's getting faster because it's moving from something more optically dense to less optically dense. So fast away, it should be moving away from the normal. So that's my refracted ray there. Okay. Now, angle of refraction, this time we've got a slightly more mathsy question. We've got the speed of a wave going from 50 meters per second to 30 meters per second as it enters a material, and it has a wavelength of 6 meters before entering the material. What is the wavelength of the wave as it moves through the material? So we should know that this happens when our waves refract. Their speed changes, but we should also know that as the speed changes, the wavelength of your wave has to change to compensate for that. So in this equation here, I've got speed equals frequency times wavelength, and both my speed and wavelength will change. So if I want to quickly answer this sub-question at the bottom, what happens to the frequency of the wave? It actually stays the same, okay, so it's the thing that stays the same. So let's see. If I plug in my original numbers, so my original speed is 50 and my original wavelength is 6 into this equation, I get 50 equals frequency times 6. So my frequency of this wave is 50 divided by 6. Okay, now it's in this new material and that frequency is staying the same. So let me use my equation again, but this time plug in my new speed to be 30, but the frequency is the same, so that's still 50 over 6, and multiplying that by the new wavelength. So if I take 30 and divide it by 50 over 6, that gives me my wavelength of 3.6 meters. Okay, now I've got a refraction question and I'm asked to draw 2 possible routes for the light and explain why I don't know which route the light will take. Well, this could either be an example of total internal reflection, or it could be an example of normal refraction. So if it were total internal reflection, then I would get this angle of reflection here, okay, which is equal to that angle of incidence. And remember that that would happen if that angle of incidence was above the critical angle. But I don't know that for sure. I don't know whether that angle of incidence is above the critical angle, at the critical angle, or somewhere below the critical angle. So it's possible that if this angle of incidence is below my critical angle, that this light ray would just get refracted out of the top into the air. Okay, and I just need to make sure for that one that that angle of refraction should be larger than my angle of incidence because my light should be bending away from the normal. Okay, total internal reflection, label the following diagrams. So my first one here, I've got that would be my angle of incidence, and that would be my angle of refraction, and refraction is a larger angle than my angle of incidence in this example because I've got my semicircular glass block, so it's moving from something more optically dense to less optically dense. Okay, my next picture, the same glass block into some air, I've got that being my angle of incidence and that being my angle of refraction. Now, since my angle of refraction is 90 degrees here, that yellow angle of incidence is actually my critical angle for this block. Okay, then an even larger angle of incidence, and therefore I've gone larger than my critical angle. So that down there is my angle of reflection this time. And that angle of incidence should equal that angle of reflection because of the law of reflection. Okay, explain the type of surface and the type of reflection in the diagram below. Name a possible material for each. Okay, so firstly on my left-hand side, I've got my incident black light rays coming in all in the same direction, hitting that surface. It's a smooth surface because it's a straight line. And then I can see all of those reflected rays also leave my surface at the same angle. This is specular reflection here, and this happens with a smooth surface, so something like a mirror. But then in my next diagram, I've still got my black lines all coming in the same direction, but then they hit different sides of this rough surface now. And at each point where they hit, I could draw little normals into my diagram. And at each point, the angle of incidence would be equal to that angle of reflection. But actually, because all of these different points have slightly different normals, I get different angles of reflection. So all of those green lines are coming off in different directions. This is called diffuse, and it happens with a rough surface, and it could be something like paper where my light is scattered off the surface of the material. Okay, refraction. A light wave travels from air to water. It's refracted. Explain what is meant by this. You should know that refraction consists of two things. It's a change in speed and direction for your wave. And here it's going from less optically dense air to more optically dense water. So it will bend towards the normal and slow down. And you could write your explanation for why it's doing that, okay, because water is more optically dense than air. What would be different if the wave were travelling from water into the air? Well, of course, in that instance, it would move faster and therefore move away from the normal. Okay, just to demonstrate what I mean, I've just drawn this quick diagram here for the first scenario where we were going from air into water, and I would advise you to draw diagrams like this in your exam if it asks for an explanation, to make it super obvious what you mean if you're saying bend towards or away from the normal. Okay, explain how sound waves are refracted travelling from air to glass. So if you've been going through these topics in order, you won't have come across the properties of sound waves in any detail yet, but you might know from the work that you've done in class that actually sound waves travel faster in more dense materials. If you don't know that or understand that, we'll do it in the next topic, so don't worry for now. But that means if a sound wave goes from air to glass, so something more dense, actually it travels faster. So if I then use my acronym for refraction, FAST, I have fast away. So actually my sound waves will move away from the normal going from air to glass, and that is the opposite way round to what happens to your light waves. Okay, total internal reflection. What happens to waves incident on a boundary between glass and air at an angle which is I smaller than the critical angle, II at the critical angle, or III larger than the critical angle? So first, if your angle is smaller than the critical angle, you will just get some normal refraction out of your glass into the air, okay, and your light will bend away from the normal. If it's at the critical angle, you will still get refraction, but now your angle of refraction will be 90 degrees, okay? That is the definition of being at the critical angle. Okay, and last one, if you have larger angle of incidence than the critical angle, that's when you get total internal reflection. So that's when you get your ray reflected back into your glass.
Okay, let's do some questions involving some of our equations for this section. So on the left here, calculate the refractive index of the following. You have an angle of incidence of 43 degrees and an angle of refraction of 35 degrees. Now, before we actually do this question, I just want to point out some of the major mistakes that people might make here. We've got a diagram here on the left showing the angle of incidence and the angle of refraction. Now, please note how those angles are measured from the ray of light. So let's look at the angle of incidence from that incident ray to the normal. And so it's really important here that you get that correct. So many pupils measure the angle which is going from the ray of light to the glass as their angle of incidence. And same for their angle of refraction, always normal to the ray of light. Okay, let's get going with this question then. So we have that equation that our refractive index n equals sine I divided by sine r. And then what are those two different angles? We have sine 43 divided by sine 35. And if I plug that into my calculator, I get 1.19. Next question, calculate the angle of refraction of the following. You have an angle of incidence and this time you have a refractive index. So we're still using the same equation here, and let's plug the information that we have into the correct spot. So refractive index 2.4 is sine of 50 divided by sine r. Now let's rearrange that equation to give us sine r. So multiply both sides by sine r and then divide by 2.4. We have sine 50 divided by 2.4 is sine r. That gives us 0.319. Then remember, in order to get r from sine r on your calculator, you have to press the shift sign button so that you get the kind of sign to the -1 with an open bracket, 0.319, close the bracket, equals, and that gives me here 18.6 degrees. Okay, what is the critical angle of a material with a refractive index 1.8 when light travels from the material towards air? So critical angle, remember, we're looking for that angle of incidence that gives us an angle of refraction of 90 degrees. And we can use this equation to help us. N is our refractive index, and that C in sine C is the critical angle. And this equation is valid when you have your light going from that material towards air. Okay, so if it were two different, if it was your material and then another different material, actually this equation wouldn't be valid anymore. N is equal to 1.8 here, and sine C is therefore 1 divided by 1.8. If it were me, I would definitely do that calculation first. So I would do sine C equals, if I do 1 divided by 1.8 in my calculator, I get 0.5 recurring. And then just like the previous slide, in order to get C from sine C, shift sine on your calculator, 0.55555 brackets, and then that equals, well, 33.7 degrees, which is my critical angle. Okay, what is the critical angle of a material with an angle of incidence of 46 degrees and an angle of refraction of 31 degrees? Okay, so first I need to use this information to tell me what my refractive index is of this particular material. So N is sine I divided by sine R. And so when I have my light going from the air into the material, I get sine 46 divided by sine 31, which gives me 1.396. Then I have my refractive index. I can now do sine C is 1 over that refractive index, which gives me 0.716. And then again, to get the critical angle from there, the inverse sine 0.716, and that gives me 45.7 degrees.
Just before we go into the tips and tricks section, if you do want some extra advice to getting that grade 9 for your GCSE, then why not download my free 20-minute exam success guide? Just click on the link in the description below. I'm going to give away all of my best advice and secrets, and completely for free. So Why not?
Okay, tips and tricks for this section. So to the normal, why have I written that? I've written that because whenever you're labeling or looking at an angle of incidence, angle of reflection, or angle of refraction, it doesn't matter. You should measure that angle from your ray to the normal, okay? Not from the surface to the ray, from the ray to the normal. Very common mistake for some pupils to make. Sound and light, yes, I just wanted to mention that that acronym FAST works for both sound and light to determine shall it bend towards or away from the normal, but it does rely on you knowing that for light waves, it is when you go from something more dense to less dense, it will move faster, but sound waves is the opposite way round. If you go from something more dense to less dense, then it will actually move slower in that less dense material. R in TIR stands for reflection instead of refraction. Pupils often call it total internal refraction. That's not correct. It is reflection, and that really helps you because whenever you have total internal reflection, then you should then know that your angle I of incidence should equal that angle R of reflection. Okay, critical angle, not for angle R, yes. So when you are talking about your critical angle, you are actually talking about a specific angle of incidence. Okay, so your critical angle is a particular angle of incidence that gives a 90-degree angle of refraction. Okay, so try not get those mixed up. Your critical angle is not the 90 degrees angle of refraction, it is the angle of incidence that causes that 90-degree angle of refraction.